Hey guys, today we'll look at the RSA algorithm. RSA is one of the public key cryptographic algorithm which uses two different keys for encryption and decryption. Have a look at this live example. The sender and receiver are going to exchange the message. For that, the receiver is going to generate two keys. One is encryption key, the other one is decryption key. The encryption key is made public and any sender is going to encrypt his message using the RSA algorithm and the public key. The encrypted message is transferred over a insecure channel and the receiver is going to decrypt using the decryption key. Now let us look at the RSA algorithm. RSA is developed by the mathematicians Revis, Shamir and Edelman. The first step in RSA algorithm is key generation. For that, let us select two large prime numbers, very large prime numbers, P and Q, and let us find out the product of them, N, which is the modulus, which is equal to P into Q. Also let us find out the Euler's torsion function, phi of n, which is equal to P minus 1 into Q minus 1. The next step is finding the encryption key, which is a public key. For that, find a number E such that GCD of E and phi n should be equal to 1. And now the combination E and n is called as the public key. The next step is finding out the decryption key. For that, find a number D such that D is equal to E inverse mod phi n, which is also equal to DE should be equal to 1 mod phi n. Now the combination D and N is called as the private key. Now let us have a look at what is this phi n is and why phi n is equal to n p minus 1 into q minus 1. The number of integers between 1 to n minus 1, that is where n is equal to p into q. The numbers which are between 1 to n minus 1 that are relatively prime to n can be given in this way. Since n is equal to p into q, the only integers which are not relatively prime to n are p, 2p, 4p in this way until q minus 1 into p. Similarly, q, 2q in this way till p minus 1 into q. That's why we can conclude that this Euler's torsion function phi n is equal to p minus 1 into q minus 1. The next important thing in RSA algorithm is the key size, which is also called as the block size. The number of bits used to represent n is called as the key size, and it's also called as the block size and can be calculated in this way: b is equal to log to the base 2 n. Well, now let us have a look at the RSA encryption and decryption process. Let us take the message to be encrypted as plain text M, and we can represent the size of this message as modulus M. Now we have to divide this message into blocks of size B, where B is the block size which we have calculated in the previous stage, which is equal to log n to the base 2. Now we can do the encryption as ciphertext Ci is equal to mi to the power e mod n, and we can do the reverse of this decryption process as message is equal to ciphertext to the power d mod n. Now let us have a look at an example by considering p is equal to 3 and q is equal to 11, which are quite a small number, and the message as 00111011. Now let us calculate the first value, that is n is equal to p into q, which is equal to 33. Now let us calculate the Euler's torsion function, which is p minus 1 into q minus 1, which is equal to 2 into n is 20. And now we have to find out the encryption key E, which is the public key. Let us consider a small number 3, which can be acceptable because GCD of 3 and 20 is equal to 1. Now let us find out the decryption key. Since GCD of 3 and 20 is equal to 1, there exists 3 inverse. So D into 3 inverse should be equal to 1 mod 20. So let us select a value for D as 7. 7 into 3 is 21. 21 mod 20 is 1. So this is acceptable. So we have the encryption key as 3 and decryption key as 7. Now let us calculate the block size. Block size B is equal to log n to the base 2. N is equal to 33. So we will get it as 6. How we will calculate this in the calculator is natural log of 33 divided by natural log of 2. We will get it as 5.04, but we will approximate it to a higher value, that is 6. Now the given message is this. Now we have to divide this into blocks of size 6 bits. So our first block is this, and the second block is this. Now let us go ahead for the encryption process. The ciphertext for the first block can be calculated in this way. The first block can be written in the decimal as 14, and 14 power E, that is 3 mod 33, which is can be calculated in this way, that is 196 into 14 mod 33, which comes to 5. Now let us see the decryption process for this block. It is 5 power, that is ciphertext to the power the decryption key mod 33, which is 5 7 times 33 mod 33, so which comes to 14, which is the message we have taken. That is the first block. So we encrypt it and we are able to decrypt it back. If you do the same thing for the second block is 3, as we understood previously, is 3 power the encryption key is 3 mod 33, which comes to 27. If you do the decryption for this, 27 power decryption key is 7 mod 33, which comes to 3. So we have done encryption as well as decryption, which is this. Now have a look at this P and Q values. We have taken the P and Q values in the previous example as a very small number, that is 3 and 11, but it is not the case in the practical scenario. P and Q, as we said earlier, the P and Q values are very large numbers. For example, P of size this, which is around 160 digit number. Similarly, the Q is also 160 digit number. Have a look at this N value, which is product of P and Q, which is a very large number. And again, the pi n, which is P minus 1 into Q minus 1, which is a very big number. So what we can understand here is P and Q should be selected such that they are very large prime numbers. Now have a look at this E, which is encryption key, which is quite a small number. Normally this encryption key is kept as a small number like 3 or 65537, such a number, because encryption key is public, which is known to everyone, so they can encrypt the message using this encryption key. But decryption key, have a look at that. It is very large number, which will not be known to any public, which is secret with the receiver of the message. So this is the way the RSA algorithm works. Thank you for watching.